Okay, last time we discussed change of basis. In this video, we introduced the notions of eigenvalues and eigenvectors. And these are some of the most powerful ideas that we'll see in linear algebra. A quick recap from a previous video. So if B is a basis in vector space V, and C is a basis in vector space W, and we have a linear transformation T from V to W, is written in coordinates by the matrix of that linear transformation TCB, which completes the square, but it makes the square commutative. For a new choice of basis B prime of V and C prime of W, we have the following rule of the change of the matrix of the linear transformation. In the special case when V and W are the same vector space and B and C is the same basis, it's sufficient to keep just one index and call it TB. So if you make a new choice of basis B prime, then the matrix of linear transformation TB prime is equal to the matrix change of basis B from B prime to B inverse times TB times matrix from B prime to B. And finally, when the vector space is the n-dimensional Euclidean space, then the formula becomes even more explicit, and the matrix of linear transformation can be written in terms of columns of basis vectors B1 through Bn. Oh, in some examples, so say no one knows how to make pants of the correct size, so all the people have to wear suspenders or belts, or at least some people. So every year 1% of belt wearers decide that they prefer suspenders, and 2% of suspender wearers decide they'd rather have a belt. So today's belts and suspenders are about equally popular, because I think they're more popular among male population. So what will people be wearing next year? In 5 years? In 100 years? Well, if the world will still be the way we know it. So let's describe this problem using the linear algebra. So we have a column vector, belts in year n+1 and suspenders in year n+1 as the following matrix, which allowed us those percentages multiplied by the column vector with belts in year n and suspenders in year n. And then there's this 2x2 matrix with those percentages in. So the diagonal entries here are the 99 and 98%, and then the off-diagonal entries are 2 and 1%. And then let's repeat this process again over and over n times. So say we have, we say it now, and then we ask what will happen in n years. So how do you compute this nth power of that matrix? Okay, that's sort of a fun example, but it's a real life example. So another example, there are many processes whose possible states are elements of a vector space. State at time n equals 0, 1, 2, 3, and so on is written as V of n. And then we have time evolution, which is discrete, right? So we have instant of moment time n and then instant of moment n+1. And then there's a linear transformation as an example before. So we call those systems as linear discrete dynamical systems, also time independent. If you wish, you can put on time dependence in that, but then it will become a little bit more complicated. So the one with the belts and suspenders shows an example. So as you understand, the statistics was taken in the United States. So again, in other parts of the world, it may be a bit different. So for the discrete linear dynamical system, like this, so V of n plus 1 is equal to A times Vn, and the state at time n is equal to A to the power n applied to the state of time 0. So in order to understand the behavior of such a system is to understand how to take powers of a linear transformation or matrix. So as an example, so let's look at the following example. So probably you know about it, the Fibonacci numbers. So we start with 0, although you don't have to, but let's do that. Then we put 1, and then we put 1. You probably know what comes next. 2, 3, 5, 8, 13, 21, 34, 55, and on and on and on. So the rule is that every number is the sum of previous two. So so you need to specify the first two numbers, and then this iteration formula goes. Now, and then again, so I know that you're smart, intelligent people. You've probably seen Fibonacci numbers somewhere, but their applications and their appearance in nature are limitless, right? I can read the whole series of lectures about Fibonacci numbers. So let me mention just a few. So if you put squares whose side lengths are equal to the corresponding Fibonacci numbers, then they form a spiral, right? So you can sort of start from this point, and then you would draw a spiral like that, right? Or like this. So you'll get a nice continuous spiral. So that's you can see some examples in nature, in flowers and plants, well, in artwork of different kinds. So yeah, so there's some beauty to that. The recursion rule Fn plus 1 is equal to Fn plus 2 is equal to Fn plus 1 plus Fn can be described by a matrix, right? So it's a 1, 1, 1, 0 written in the basis like that. So it's the state at the next for the next position for next n as a linear transformation applied to the state at the previous position. So since we have decided to pick f1 equals 1 and f0 equals 0, then you can write it like this. So you need to act with the matrix 1, 1, 1, 0 to the power n on the column vector 1, 0. So another example where Fibonacci numbers appears in a population of creatures, right? So every month, each creature older than 1 month reproduces, creating one new creature. That's what happens in these populations. For example, it appears in colonies of bees, of bumblebees, right? So the male drones, they don't have kids, right? So they have the male and female bees, they reproduce differently. So if you do it like that, you can count using this formula. So population at instant moment n will be related to that at moment n plus 1 by this matrix. And in fact, that's how Fibonacci found his numbers, right? So people were working with honey a long time already, and so he knew about this count. So you need to know how quickly the bee colonies will grow. Yeah. So we have reduced the problem to the matrices. So in order to understand a linear discrete dynamical system given by this linear transformation, we should compute the nth power of this matrix. So if the matrix A from Rn to Rn is given by a diagonal matrix, that's easy, right? So you just exponentiate, you just calculate the nth power of all of the diagonal elements, right? So it's an easy exercise when you multiply matrix by matrix. If it's a diagonal matrix, that the diagonal elements only get multiplied by themselves. Now, a matrix is diagonal if and only if for each EI from the standard basis, there's a scalar lambda I, so that A times EI is equal to lambda I times EI. So the entire action of the matrix is reduced to simply multiplying by a scalar lambda I to that matrix. So for 3×3 matrix, we'll have a diagonal matrix with a lambda 1, lambda 2, lambda 3 located on the diagonal. In this case, so it's almost as good for A to be diagonal in some basis. Say there is a basis B, with elements B1, B2, and so on, Bn. Since this is the case, we can change basis to B, compute powers of the diagonal matrix in that basis, and then come back, because we know how to make a change of the basis for the matrix. Note that the A is diagonal in the basis B only when the formula from the previous slide happens, namely that multiplication with the matrix A by vector Bi is given to by lambda I times Bi. So let's see what happens in other bases. If matrix A is from Rn to Rn and is given by the matrix, let's also call it A, and if script B, B1, B2, and so on, Bn is a basis, so set matrix B to be formed by whose columns are vectors from this basis, B1 through Bn, such that the matrix VB is equal to B inverse times V, right? So for every vector V, and matrix AB is equal to, as we know it from the previous lecture, B inverse A times B. And then hence the A, and so you can now reverse this last equation. You can multiply by B on the left and by B inverse on the right to get this formula. We can compute the square of this matrix. So we just multiply this expression by itself. We have B inverse times B in the middle, which will cancel off. And that will bring us B, A sub B squared times B inverse. And then, of course, it would work for every integer power. So if you can find the basis B such that the matrix is diagonal, we can easily compute its nth power. So the nth power of the matrix, and therefore the nth power of the linear operator. Now let's introduce eigenvalues and eigenvectors. So A is diagonal in the basis B exactly when A multiplied by Bi is equal to coefficient lambda I times Bi. Any vector B such that AB is equal to lambda B is called an eigenvector of A, right? So it's a German word. You know, in German, so they tend to merge words together. So of course, in English it would be two words. Let me know in email what's the Chinese word for that. So it's eigen means proper, like it's like a proper vector of A, right? It's sort of it's the vector which belongs to matrix A. In this case, and lambda is called an eigenvalue. So B is eigenvector and lambda is an eigenvalue. That's the terminology. So take an identity matrix. Now every vector of this matrix is an eigenvector, as we know, since I acting on V is equal to V, and the eigenvalue is equal to 1, right? Because that's what lambda is equal to. Take matrix 2, 0, 0, 3. Diagonal matrix. So we have A acting on E1 gives 2E1, and A acting on E2 gives 3A2. So both vectors from the standard basis are eigenvectors. and the vectors, and also vectors with any multiple, multiple of those. So A times E1 and B times E2 are also eigenvectors for any scalars. Question, are there any other eigenvectors? Well, let's ask, right? So let's do the multiplication and then demand that this is equal to lambda times AB. And then we need to solve the system of linear equations. So clearly this happens only if A equals 0 or B equals 0, right? Thus, the only eigenvectors are proportional, are those which are proportional to the canonical basis vectors. And the only eigenvalues are 2 and 3. Now consider matrix A, which is 2, 1, 0, 3. So since A times E1 is equal to 2E1, the vector E1 is an eigenvector. That's good. Therefore, as well as its multiples. So E1 times 1000 will be always also an eigenvector. How about other eigenvectors? So, and eigenvalues. Well, if the matrix is not diagonal, it's not quite straightforward to do, but nevertheless we can. So let's see how this works. Now the equation A times V equal to lambda V is equivalent to A minus lambda times the identity matrix multiplied by V is equal to 0. We simply move this to the left hand side, and we talked about. And now we can think of the system of equations as an homogeneous system of linear equations with a matrix A minus lambda I. As we know from first week of the class, then that there is a non-zero solution if and only if the determinant of this matrix is equal to 0, right? So if rows are linearly dependent. So, and this statement can be used in order to find eigenvalues. So lambda is an eigenvalue if and only if it solves this equation. This is called the characteristic equation. Let us try characteristic equation. So determinant of A minus lambda times I equals 0 for this matrix. You can pause the video and do the calculation by yourself. So here it's possibly 1 minus lambda is equal to squared is equal to 0. So it will be a polynomial. The left-hand side of the characteristic equation will be a polynomial whose degree is equal to the number of rows or number of columns of the matrix. It's a polynomial in lambda. Take this matrix, compute its characteristic polynomial. So you're going to get 2 minus lambda times 3 minus lambda equals to 0. Now let's take this off the non-diagonal matrix. 2, 1, 0, 3. Do the calculation, and voila, we have the same characteristic polynomial, right? So, well, the reason for it is because when you calculate the determinant, there's a 0 here, and then the 1 which stands off the diagonal does not change the calculation of the determinant. So eigenvalues will not change, but the eigenvectors will, as we'll see momentarily. And then this matrix, which we used in the for our dynamical systems and Fibonacci numbers, 1, 1, 1, 0, will have the following quadratic polynomial: lambda squared minus lambda minus 1 is equal to 0. Now let's get back to this matrix from the third example from the previous slide. So we have concluded that the standard vector E1 from the standard basis is an eigenvector, as well as its scalar multiples. How about other eigenvectors? So there should be, right? Because the characteristic equation is that, and it has two solutions. So one solution we already talked about, it's the eigenvalue lambda equals 2, and eigenvector is E1. So what is the corresponding eigenvector for the eigenvalue 3? which is the second solution. So in order to find the eigenvectors of A of eigenvalue lambda, it means to solve this equation, right? So it means, or in other words, finding the kernel or the null space of the matrix A minus lambda I. So we first find eigenvalues, and then once we know what eigenvalues are, next step would be to find the eigenvectors. So we know that the second eigenvalue, one of the eigenvalues of this matrix is 3. Now, that it means that if we subtract A, if this matrix is A, so A minus 3 times identity matrix will be given to this matrix, negative 1, 1, 0, 0. So which means that we need to find the kernel of that matrix. In this simple example, it's clear that this kernel is spanned by vector 1, 1, right? So if you multiply this matrix by this vector or its scalar multiples, you'll always get 0. Now let's check that the original matrix, so this is indeed the eigenvalue for the original matrix. So we'll do the multiplication, you get 3, 3, right, which is 3 times the 1, 1 vector. And 3 is exactly the eigenvalue. So this perfectly checks out. Time for exercises. So there's obviously homework, but if you're watching it for the first time, I advise you to do exercises as well. Take matrix 1, 1, 0, 0, eigenvalues and eigenvectors for this matrix, which controls Fibonacci process. So we already saw that the characteristic polynomial is lambda squared minus lambda plus 1, and it has 2 roots. They are irrational, 1 plus minus square root 5 over 2. So probably some of you know that this is the famous golden ratio, like the one with the plus. So yes, there is so the reason why this Fibonacci spiral is so nice and elegant is because it reflects the golden ratio. So once we find the eigenvalues, now let's find the eigenvectors. So here they are. The eigenvalues are lambda plus minus equals to 1 plus minus square root 5 over 2. So we need to find the kernel of this matrix. So it's matrix of the matrix itself minus lambda times the identity matrix, and that's what it will look like. Well, and then yes, you can check that if you take this vector here, so you put lambda plus minus, right, and then 1, then it will do the job, right? So both roots of this symmetric polynomial will go just fine. So lambda plus 1 and lambda minus 1, as well as their scalar multiples, are the eigenvectors. Okay, get back to Fibonacci. So remember, we wanted to calculate what happens like in n steps, like or in many steps. So one step is controlled by matrix 1, 1, 1, 0. N steps are controlled by this matrix to the nth power. Now, these 2 vectors that we discovered on previous 2 slides before are the eigenvectors for matrix 1, 1, 1, 0 with eigenvalues 1 plus square root 5 and 1 minus over 2 and 1 minus square root 5 over 2. In other words, in the basis, in this given basis, the matrix 1, 1, 1, 0 becomes diagonal with entries lambda plus and lambda minus on the diagonal. So that's what it looks like, right? So that's lambda plus and lambda minus on the diagonal of the matrix in the basis where where it's diagonal, right? So these are the eigenvalues, lambda plus and lambda minus, and then as we discussed, the in order to find the matrix in different bases, right, we multiply by the matrix, so by matrix which changes the basis on the left and the inverse of that matrix on the right. So the basis, the coordinates of the vectors in the eigenvectors are given by lambda plus 1 and lambda minus 1. So that's our matrix of change of basis. And then we multiply by this on the left and multiply by the inverse of this matrix on the right. And you can check that this calculation works out. Okay. Now this is the case for one iteration, for one step in the discrete evolution process. Now let's do it for the nth power. So as we discussed, so in order to find the nth vector, what happens after n iterations, we'll take the nth power of the matrix in the diagonal form. So we know that it's easy to calculate the nth power of the diagonal matrices simply by calculating the nth power of its diagonal elements. And then we need to conjugate it. We need to multiply it with the left by the matrix of change of basis, and on the right by the matrix inverse that. And then if you apply this to vector 1, 0, which were the initial conditions, the first two numbers in the Fibonacci sequence, we will get the answer on the n step, right? So the vector which is formed by fn plus 1 and fn